Okay, super cool. Hi everyone. So good to see you. I'm Julius, and I have my colleague here. Um, Jeff and I are from. Hi Feng. So good to see you again. Um, Jeff and I are from the same company called Hubble. We are a construction tech company. And we'd like to share with you some of the challenges that we run into as we lead the team, as we try to optimize the engineering processes. And hopefully, you could take a thing or two from this presentation that we're going to have. And of course, we'll try our best to answer any questions that you may have towards the end of this talk. Um, with that, let's jump right into it. So the way we are going to talk about this is that we are going to first talk about the difficulties that we run into in how we scale our team, and how Jeff and I were able to propose a solution which we felt uh, help us in terms of how we manage our engineering team, and how we are able to make things much more effective and make things much more actionable. So here's a brief background about our company. We actually started off about 2 years ago, whereby the size of the company, or at least the engineering team, is somewhere about maybe 5 to 10 people. Hubble is a construction tech company building a software as a service solution for construction projects, and we have customers in Singapore, Malaysia, New York, and several other countries. Um, and as the industry grew and the company grew as well, and over time, right, we actually grew to about this size from somewhere about 5 to 10 engineers. This year we have about 35 engineers. So back then, one of the easy thing that we could do is to actually find out how we can find out who's doing well, who needs some help, where's the bottleneck. But as a team grow to this size where you have layers of managers and you have the various teams running concurrently, it becomes more and more difficult for us to actually say, hmm, why is one team slower than the other? Is the mobile team doing fast enough? Is something wrong with the backend? Is someone spending too much time at work? We need to find out all these things, because all of these has certain implications on how we can keep people happy, keep people engaged, and also be able to find out what resources that we need, so that I can go to talk to the finance manager, to the CEO, to say that, hey, we need more resource in order to fulfill the need of the product. The good thing about Hubble, and I'm pretty sure in most companies out there, including your company, is that there's data everywhere. There's so much data that we can use. And for many companies out there, we are probably at an early stage whereby we are not using enough of it to help lead the team. For us software engineers, perhaps the most famous product that we use to check in our code is probably Git, right? You have all sorts of versions of Git. For Hubble, we are using a product called GitLab. As you probably know, it's a CI/CD solution, it's a DevOps solution, and part of it is actually a code repository storage, and that's what we are using. So as a VP of engineering at Hubble, there are various things that I always think about. One of the most important thing that a VP should do, at least a VP of engineering, is to make sure that people are as productive as they could be. So I go around and try to make sure that people are relieved of their blockers, and also people feel engaged. A research done in 2013 shows that if a company has a bunch of engineers, or in general a bunch of staff that are engaged, they will highly likely outperform their competitors by as much as 147% per share. What that means is that for every one person, you get the productivity of another person for free, and another half a person for free. So for every one person, you get 1.5 times his productivity, so long as he's engaged. So that's a lot of cost savings. And also, you do a lot of good to the person himself, because then if you are engaged at work, you tend to actually contribute more, you feel more recognized in your work, and you feel more fulfilled yourself as well. So it's important for me to think about how can I help the team get engaged. So what research that was done by Microsoft, which was presented in Wharton, shows that the moment the amount of overtime spent by any staff goes beyond 20%, there's a 1.6 times increase in disengagement. So that's a lot. What that means is that if we spend too much time working, especially in COVID-19 situation, right? I know Hong Kong things are great, things are fine, but in many other countries, things are not as good as Hong Kong, and people have been reporting burnout all over the world. So what we are doing here is to simply say, all right, for my entire team, how many of them are actually committing their code outside of work hours, and how many of them are actually committing their code within work hours, and we're getting that percentage to kind of see what's the percentage of work that are done outside of work hours. These are good proxy. These are not like, actual work that was rendered, but these are good enough indications for us to ask questions. So this is actually a real data in Hubble, whereby we have seen over a period of 2 years, the amount of activities outside work hours has increased from somewhere around 7.5% to 15%. What we can expect then is that if the trend continues, things are going to get worse for Hubble. And so this will be a good opportunity for me to take a step back, talk to the CEO, talk to the VP of product, talk to the HR manager to say that, hey, this is not sustainable. We have to slow down our pace so that we can have a better quality of life for our engineers. Here's another thing that I always think about, which I'm pretty sure in most of your company you also think about as well. How do we protect the company from knowledge decay? Here's usually what happens. Whenever a person leaves the company, there's a certain amount of knowledge that will be lost, and you have to take time to actually figure out what was lost. And that's because, with all sort of things that you cannot ask the person anymore, and you don't even know whether the person knows or not, and the person could be busy and so forth. You can no longer engage the person as you used to when he or she was still in the same company as you. So in the tech industry, there's this interesting term called the bus factor, whereby the idea is you try to find out how many engineers needs to be run over by a bus for the project to fail. You can actually use this kind of analytics on your Git repositories as well. What we did in Hubble is to try to find out how many times a person commit for a particular project, and we try to see the leaderboard. So here, for example, if you look at the item on the right, you can see the one on the green box. You have John, Cheryl, and Sandy, whereby the difference between the number of commits that they have is generally not too much. Which, what that tells us is that the project is still safe, because even if one of them leaves the company, at least two of them can still keep the project running. If you look at the one with the brown box, number 4, you have Dawson, and then you have Pradeep and Vishal, who has a significant amount of knowledge gap from Dawson. Again, you can see the amount of commit of Dawson is somewhere around 2,502. Pradeep and Vishal, on the other hand, the number of commits is only around 300 each. So if I see this, I can straight away go to Dawson and say, instead of actually assigning work to yourself, you can assign it to Pradeep and Vishal so that they can accumulate knowledge on the project, and that will help me de-risk the project. If you look at number 5, you have Enrique, Carl, and Pragati. And the interesting thing is, Enrique and Carl both resigned from the company. So the company will be in great danger if Pragati leaves the company as well, because there's nobody else to take over. I mark it as red, as a red box, so that it would be helpful for me to say, this project is in danger. I might as well bring other people into the project to quickly de-risk, so that if Pragati falls sick, if Pragati leaves the company, we will still have someone to actually sandbag the problem rather than fixing it when it's too late. Uh, Interestingly, as many of you probably might not know, for people in the senior executive level, we don't have this kind of visibility. And a lot of things are lost in translation. A lot of things are lost in communication. So if we have this kind of visibility, we can ask all sorts of questions and engage the team so that we can find out what problems we can solve before it actually surfaces. Here's another one. One of the things that I also think about is how fast are we delivering? Are we slowing down? Are we speeding up? How do we measure? Many a time, what you're seeing in companies, especially in bigger companies, is that it will be some form of one-on-one communication between the manager and the one who's directly reporting to him. And if you have layers of manager, it becomes more complex because everything is just about feeling, you know. So what we did in Hubble is that you can actually create a value stream analytics, whereby a typical practice when you check in your code is somewhere like this. You write a bunch of code, you commit your code, and then somebody has to you commit your code, you create a pull request or a merge request if you're using GitLab, and then somebody else review the code. And they review the code, they're like, good enough. Then they merge the code, and then it takes time between the merging of the code for the code to actually reach production. So I can actually see week over week or month over month what's going on. Um, all those three steps has to go down over time. First commit to PR as in pull request to merging of the code and merging of the code to deploy. Here, as what we are seeing here, we can see that the time that it takes for a pull request to be merged is actually growing over time. What this indicates to me is that I can actually go to the tech lead and say, "Hey, what's going on? Perhaps there are a lot of newcomers. Perhaps there's a lot of bugs. Perhaps we are lacking manpower, so on and so forth." With this very objective data that we can take a look at, we can actually take action straight away instead of waiting on the side trying to figure out and complain why things are slowing down. Now we can take concrete action because data is available, and all of these are shown from GitLab. Here's another one. One major concern, especially by QA, by product, and also by the customers, is the amount of bugs that they experience whenever they use the product. So, as an engineering manager or a VP of engineering, and even as an individual contributor, you actually keep thinking about how can I reduce the defect density. So, interestingly, research was done by Cisco and SmartBear, whereby they found out that for every commit, the amount of lines of code that has to be in the commit should be 250 or less. 250 lines of code or less. And here's the idea. If you try to review a pull request, for example, and then you see, a bunch of code, if it's too long, the longer it is, the more likely you're going to say, it looks good to me. You can just, merge the code. And that's just because of the human nature of us having very limited cognitive load. The lower the amount of lines of code that you ask somebody else to review, the better a job they can do for you. So this is a sweet spot. In Hubble, it's important for us to track this as well. Again, as you can see, these are all scientific studies, and we're simply converting scientific studies to actual things that we implement in the company. So here's one of the graph that we have in Hubble, whereby for each engineer every week, we are tracking the average lines of code that they are committing. So this will help me say that, okay, Anthony seems to be doing quite good, the second column here. But Bella and Dawson and perhaps Janice needs a bit of help. So it's very easy for all of us, and this is open to everyone in Hubble, by the way. It's very easy for the engineers to say, I'm doing good compared to my colleagues, or I'm not doing as good compared to my colleagues and have to improve. This will also be a good opportunity for their managers during one-on-ones to talk to them and say, hey, this is the KPI that I want you to achieve next time because you're not doing as well compared to your other colleagues. So here are some examples that you can actually do yourself. And in fact, many of you who has been doing DevOps, for example, might be asking, what about the DORA metrics, right? For many of you who have been following Google Cloud, DORA is actually a bunch of lagging indicators, the DORA metrics, and I will show you later what they are. Lagging indicators actually tell you things, uh, the current state of affairs, but leading indicators are the one that I have shown you just now. These are the indicators that will say that if these things continue to happen, upwards and downwards, it will lead to uh, uh, how should I say, the lagging indicators, which I will show later on. Um, the DORA metrics is actually composed of four. These are the indicators by which a software engineering team is performing well or not, whether it's a startup, whether it's a big company. This is very well studied, and this is documented in a book called Accelerate, which you might be interested to see after this talk. And of course, if you go to Google Cloud, the Google Cloud website, you can see this as well. So the DORA metrics is composed of four: deployment frequency, lead times for change, time to restore service, and change failure rate. I'll show you how we are computing each and every one of this using our GitLab repository. First, we look at the change failure rate. A change failure rate is the percentage of deployments causing a failure in production. So we want the amount of failure rate to be as low as possible. So say, for example, suppose I release a 1.0 of my product. How many hot fixes do I have to create in order to fix the bug that exists in 1.0? We don't want that. So uh, uh, in a typical cycle, you probably want to have 6 or 7 releases without a hotfix. So this is an actual data from Hubble, and what it's telling us is that Hubble is not doing very well. We have a lot of hotfix, which means that things are getting slowed down. Our software engineering quality is not as good as it can be. Before we have this data, we don't even know. Now that we know, now we have to take action. And for 2022, this would be a very important goal for the engineering team to actually hit. Here's another one. Mean time to resolve is the amount of time it takes for you to actually deliver a release that was, or deliver a hotfix in the event that a bug was found after a release. So how we are computing this is that in Hubble, we are using semantic versioning. For those of you who are not sure about what semantic versioning is, it's how you version your software or your releases as a 1.0.0, 1.0.1. So a semantic version that ends with a zero means that it's a stable release. A semantic version that has a point 1, point 2, point 3, we use it to indicate that there was a hotfix. So what we are doing here is that we are trying to measure the distance, the amount of time it takes between a hotfix and a stable release, or at least an assumed stable release. So when we subtract that number, then we get the average. That's the average amount of time it takes for us to render a fix. In general, you need to resolve things as fast as possible. For Hubble, we say that it has to be a day. The reason why it has to be a day is because we are measuring the amount of time it takes for Apple to approve our iOS product as well. So that's roughly the benchmark that we set for ourselves. However, if you're doing backend, you can actually deploy anytime. So for backend, it should be as fast as possible. In general, a few minutes or a few hours after an issue is found. So this is one way that we can do it. There's also a change lead time. The change lead time, the idea here is that every time you fix something, every time you create a feature as a software engineer, you want your customers to actually experience it as soon as possible. The longer it takes for that piece of code to be actually released to production, the less value it is, right? Because it's just sitting there and doing nothing. So we want to measure that. In Hubble, we are doing a weekly release. So in general, you want to have a change lead time of around 7 days on the average. Anything above 7 days tell us that we are slowing down. Perhaps we miss a release, perhaps something happened, and anything below 7 means that there's a lot of hotfix. And this is actually a real data from Hubble. What we have seen is that we have a lot of hotfixes, which is not good at all. You can argue that in a startup it's okay, but it's still not good. We have to reach a point whereby we have as little hotfix as possible because it slows down the engineering team in general. So for Hubble, we set it at 7. And so for us to actually figure that out, it's just the distance between the creation date of two tags. So every time you release software to production, you actually tag it in your repository, right? So it's just the delta between the one tag over the other. Then you get the average. Then that's the change lead time. Another one is deployment frequency. Deployment frequency tells you the number of, or the frequency of deployments, the frequency of releases that you're actually sending out. So for Hubble, we want to have one tag per week. So in a weekly graph, you want to have only one tag. per week. So what we are seeing here is that if you have more tags within a week, it means that you have so much hotfixes, and that's not good. If you have less, it means that you're not releasing on time, which is also not good. So all we have to do is actually measure the number of tags that we are creating within a week, and then that becomes our deployment frequency. Um, Jeff will be discussing how we were able to do it using perhaps Google Cloud or AWS or all sorts of cloud technologies that you're using right now. With that, I'll be handing over the microphone to Jeff.
Thanks, Julius. I will be sharing the slides on my end. Perhaps you will just provide me a verbal confirmation that we'll be able to see it. Just one moment, yeah. Okay, Julius, are you able to hear me? And also, are you looking at the analytics stack overview?
I can hear you, but I think Oryx will have to change the shared screen.
Got it.
I can see it now.
Okay, thanks, and hello again to everyone tuning into the talk. So earlier on, Julius has actually discussed all the matrices that Hubble has utilized in order to measure software engineering efficiency. Now, with that, right, this sort of analytics would not be possible without the underlying data, and I would target to spend the next 10 minutes to basically describe how we actually build our pipelines to actually to funnel in all the data necessary to display the matrices via our visualization tool. So I'll start off with the overall stack, starting from the data source collection. Now, because we are using a GitLab Cloud, we don't actually have the data residing in a localized database server. So with that, we rely on the REST APIs that are provided by the GitLab community and developers. So if you try and Google GitLab v4 REST API documentation, you'll be able to see various API calls to get various information, whether it's about getting the repositories, also known as projects, getting the list of names of GitLab contributors associated with the releases and the commits. Those are the URLs that you want to leverage. And when you try and use something like, if you try and use a Python request package to basically call the URLs and get the data in, you will receive this data in a JSON format as shown in the small screenshot on the bottom right of the slide. So with that, how do we actually process this form of data, which is considered semi-structured? Ideally, when we want to analyze the data using SQL, we want them to be in tabular or columnar format. So following that, we can use the pandas package to actually convert the data that's in JSON structure into a data frame. So it's very similar to a table. And with the same pandas package, you can actually store this data into a CSV file. So how we actually partition or rather group the CSV files in Hubble is we group it based on the context of the data from GitLab. So any information with regards to the commit would be stored in a single file known as commits underscore timestamp, because we do pull the data on the daily basis to capture any changes to the GitLab repositories. So once you pull out all these CSV files, we will then be able to store these CSV files into object-based cloud storage solution. So when you're using a Google Stack, right, you can use Google Cloud Storage to actually store those CSV files. And this is where the raw storage layer is. Then next, how do we actually warehouse this CSV file data that's residing in the CSV files, right, into a table or tables, you could actually make use of existing Google Cloud Python APIs available for use to read the corresponding CSV files and write them into the respective tables. So whenever you have, let's say, a commits CSV file, I would use the Python APIs to actually read those records and populate into a data warehouse table known as commits. So whenever new data actually comes in via new calls and subsequently new CSV files, you will do the corresponding updates or insertions of the records accordingly. So in this stack, we've shown Google BigQuery as the data warehouse solution. And then finally, once the data has been stored in the data warehouse tables, you will then be ready to use any sort of data visualization tool that can connect to Google BigQuery in this example. So in this presentation, we are basically showing Metabase as one of the proposed solutions. Metabase is an open source data visualization tool with multiple connectors, and one of them being the Google BigQuery tables. So with that, now we have actually covered from the point of data collection, storage, as well as analytics. So how do we actually automate all these individual steps? So in order to automate all these steps, we basically used the Apache Airflow project. That is the open source solution for one of the several open source solutions to orchestrate data pipeline tasks. So if you see, do pardon the very small fonts in this image, because our job actually pulls in a lot of data, a lot of dimensions as well. Basically, each that task, each block is known as a that task, which performs a particular task. It covers from the point of API call, where you collect the data, transforms the data into a data frame, and then storing it into a CSV file, moving the CSV file to the corresponding file storage URIs, and then subsequently reading of the files into the data warehouse tables for the purpose of insertion and updates. The next few slides basically shows a snippet of some of the data modeling that we've actually done for for our individual tables. So this is basically one example of how we actually join the relationships between the main merge request tables as well as the individual tables for whereby you can see the details of the authors associated with every single merge request, who has the merge request been assigned to, who has reviewed it, and also who has merged or closed the particular item. And this is another example or a basic example of some additional snippets of the data modeling. Some of these tables actually are manually populated. For example, at the point of development, there is no how should I say? There is no field in GitLab where you can actually declare which particular team you belong to, or which particular sub projects based on the context of the organization that you're working in as associated with a project. So normally how we work around this is that we try to analyze data and we see how a particular team is performing, or how a particular product is being developed over time. What we normally do is that we will actually create separate CSV files. And from GitLab, we know what the project ID is. Every single GitLab repository has its own ID, which is in numerical format. And then we just create a CSV table. So this project, this is project ID 123. And then in column B, I will actually put in values like back-end team or front-end team. In the case of a team name mapping, or I could put in values like point of sales or marketing, for example, when it comes to for the products side of things. So we'll populate all this information, and then we'll subsequently upload this into cloud storage as well on a manual basis, and then subsequently run similar codes to update those a similar data warehouse table, and then from a data analytics point of view, you would then establish the joins accordingly. Now, throughout the course of the pipeline development, we have observed several key challenges, and I would like to take this opportunity to just share two of them. So firstly, is the fact that depending on some of the transactional data that we're pulling, and in this particular case, it's the commits table, or rather the commits API, we see that sometimes the same person may issue or rather create commits using different names. So this one reason that could potentially happen is because of carrying out commits using different machines. So on the left side of the slide, you will see that there's an example of this person named John, right? And the person's company email is john@mycompany.com. So we see several commit records whereby the author's name is John and the author's email is john@mycompany.com. Then over time, we tend to see sometimes changes in the name. Now the name has been expanded to include, for example, the additional last name, John Wick, for example. But because the company email is the same, our understanding is that this group of these subsequent commits also belong to the same person. But if you look at the commits, the response structure of the commits API alone, right? There is no, I would say, unique identifier that is tagged with it. The unique identifier, in fact, right, is actually found in another API called known as billable members ID. So in order to circumvent this challenge, right, what we have done as part of the initial setup, also the initial load, is that we actually compile a list of different combinations of name and emails, and then we actually have to check in with every single software engineer that there is, and confirm that this belongs to these credentials actually belong to that person at that point in time. Then we'll actually populate a third column, which is a unique identifier known as billable member ID, which matches with the response structures you get from calling the billable members API. Basically, just to clarify, on the left-hand side, you can see that even though they have different names, we populate the same billable member ID, so that whenever we start to join the commits records, right, we are able to join it to one single identifiable person via a members lookup table. So this member lookup table, if you see on the right-hand side, it is an ER diagram. The middle table has a very similar structure as what you see on the left side of the slide. Now, number two is actually a pretty well-known challenge faced by many developers when they would like to extract data via APIs, especially when it involves a request to put in large amounts of data. So when there are large amounts of data, the responses are usually paginated depending on the services that you're calling, be it GitLab or any other product. They have its own way of identifying whether they are subsequent pages, and if you would like to pull data from the following page, what sort of variables are you supposed to substitute with in your subsequent call. So one example we use here is that for every request that we send out, every response that comes in, it has a header. And in this case, the header is known as x-next-page. So if whatever data you're getting is has a value of true for x-next-page, then you would put this code in a while loop. So as long as that header is always true, I will then increase my my query parameters, right? The page number as part of the query parameter by 1, for example. So this is one example. There are many ways of also managing how you want to pull data from response structures that are paginated. And of course, when you finally reach the last page, the labels will usually return a null value. And when that happens, it will proceed to break the loop, and this is where the ingestion stops. And everything gets, all the information gets house kept into a CSV file. Any duplicate records will then be cleansed, and that will be tucked into a CSV and stored into the cloud storage, and then subsequently processed into the data warehouse. Okay. Now, I reached the end of the slides on the BI stack. I am sharing a list of API URLs, which I believe you would find very useful to put information that is very relevant to the DORA matrices that my colleague Julius has shared earlier. So it's about 2 slides long. And if you'd like to understand more about how, what sort of query parameters each calls can accept, what are the kind of, what are the fields or rather the response requests you're getting, do visit the API documentations to learn more about the details. So with that, we conclude our presentation. Thank you.
Thank you, Julius and Jeff, for the amazing presentation here. And I think most of our audience got no questions for you guys so far. So just in case that if anyone is interested in asking questions to Julius and Jeff, you can always type some comment in the comment section of the YouTube live and Facebook live. So yeah. So thank you, Julius and Jeff, and